Hello, my name is Ted Weathersbee, and this is the final presentation for E&ME 475 Robotics in the fall 2020 semester at UMBC under Professor Wu. Welcome to a presentation of a paper on the design of an economical SCARA robot for industrial applications. This outline represents the path that will be taken during the presentation. After introducing the paper and outlining what a SCARA robot is, we will move through the robot's creation process, discussing the project design goals, the kinematics behind the robot, and the design process that outlined its creation. After that, the testing of the robot, along with experimental results, will be covered, followed by a conclusion. Robotic manipulators have become a large part of the world today. As we work to automate the manufacturing industry, among others, the wide range of application for these machines has been highly sought after. Research on robot design includes topics such as nonlinear direct power transmission, which moves motors from joints to the base of the robot to decrease the effect of weight on the robot's dynamics, and vibration control in SCARA robots, or how the elasticity of harmonic drives affects the vibration of a SCARA robot in use. This paper is a study on the design of an industrial SCARA robot with a focus on cost effectiveness and keeping in competition with commercial SCARA counterparts. What is a SCARA robot? SCARA stands for Selective Compliance Articulated Robot Arm. The selective compliance section of that refers to the fact that it is compliant in the XY axis and rigid in the Z axis. The articulated robot arm part signifies the strength of this robot, which is what it's used for small assembly applications. Due to its high accuracy and repeatability, the SCARA is a popular choice for commercial applications. A defining aspect of the SCARA robot is its 4 degrees of freedom. As you can see in this top right figure, the SCARA design has 3 revolute joints, which are labeled as J1, J2, and J4 in this image, and 1 prismatic joint, shown as J3. The goal for this specific SCARA robot, the FUM SCARA, was to make a manipulator that could compete with well-known SCARA brands in terms of effectiveness, while at the same time keeping costs down and materials realistic. Table 1 highlights the FUM SCARA compared to other SCARA brands. As you can see, the stats from the FUM SCARA are very competitive, even boasting the best values in both J1 plus J2 linear velocity and repeatability in the XY plane. Determining the Dennevit-Hartenberg parameters is the first step to finding the kinematics of a robot. By using the DH convention, coordinate systems were laid out on the robot, which is shown in Figure 2. After that, by looking at the relationship between each coordinate system, the DH table for the FUM SCARA was established in Table 3. The DH table describes kinematics using the variables labeled in the bottom right. Using the DH table, values were able to be plugged in following the equation below to obtain transformation matrices. Each coordinate system or reference frame will have its own transformation matrix to represent how that frame moves in a three-dimensional space. By combining all 5 of the transformation matrices, as seen in equation 2, the compound transformation matrix for the FUM SCARA can be found, which describes the movement of the entire robot arm as a whole. Equation 3 represents the compound transformation matrix, and it can be better understood using the key at the bottom of the slide. Using the compound transformation matrix and equating it to equation 4 depicted here, equation 5 can be derived, which describes the position of the end effector. By solving equation 5 for x, y, z, and gamma, 4 closed-loop expressions can be found. This completes the kinematics of the robot by representing the inverse kinematics, as opposed to equation 3 and 5, which represent the forward kinematics. The Jacobian is a link between the joint velocity, in this case theta dot, and end effector velocity, which is typically x dot, or in this case v for velocity. In equation 6, you can see that link represented. Using equation 6 and the previous equations, equation 7 can be derived to represent the Jacobian of the robot. To start the mechanical design process of the robot, the first stage was the selection of the motor and the gearbox, otherwise known as the transmission system. The goal for this system was to transfer power into machine movement effectively. In Figure 3, the process used to arrive at a transmission system is outlined in a flowchart. After estimating variables such as link weight and link length in initial concept design, different transmission systems were tested on a critical trajectory. The critical trajectory was designed to expose the machine to the maximum velocity and acceleration it would experience, and the system was tested on this trajectory to ensure the robot could handle prolonged or heavy usage. After several iterations, the test simulation that best matched the calculated results was chosen and implemented. After selecting a transmission system, the next step was joint design. For the first joint, which attaches the first link to the machine base, there was a heavy focus on not exposing the gearbox shaft or any part of the transmission system to any bending moments. This was accomplished by inserting supports on both sides of the link to support it evenly without the help of the gearbox. This can be seen in Figure 4. In this design, the motor torque transmits to the first link through the use of a power lock instead of traditional methods. For the second joint, between the two links, the same major focus existed. It was not to expose the transmission system to any bending moments. A number of concept designs for the second joint were drawn up and can be seen in Table 4 below. Critical design elements such as joint weight and link stiffness were considered, but perhaps most importantly, the joint range was valued highly. Ultimately, the joint option farthest to the right was chosen for its low joint weight and high link stiffness while maintaining an unlimited joint range. For joints 3 and 4, they're located right next to each other, since they both control the end effector, just in different ways. J3 and J4 control the linear and rotational moment of the end effector, respectively. One important aspect of the joint design in the FUM SCARA is the use of a ball screw and a ball spline as opposed to a traditional rotary ball spline. While these both accomplish the same thing in the end, a rotary ball spline translates both linear and rotational motion at the same time, while a ball spline combined with a ball screw will translate linear motion through the spline separately from the rotational motion which gets translated through the screw. What this means on the production end is a reduced joint size and a more complicated design using two parts for what could be accomplished with one. The big takeaway from a design perspective, however, is the reduction in cost that this choice brings to the table. You can see the contrast between these two systems in Figure 5, where the FUM SCARA uses a combination of a ball screw and a ball spline, whereas the Epson LS SCARA uses a special ordered rotary ball spline. If you recall, in the simulations of the FUM SCARA, when determining the transmission system, a critical trajectory was simulated. As you can see in Figure 6, this is what it looked like. The design of the trajectory takes the robot from one corner of its workspace to the other, and the highest forces are exerted on it when the two links are collinear, which is right in the center of Figure 6. MATLAB software was used to simulate the effects of the trajectory, so when the links are collinear, this is when each link reaches both its maximum velocity and its maximum acceleration. In addition, due to the center of gravity of each link being the farthest away from the base at that time, the machine also experiences its strongest lateral forces during that moment. During joint design, one of the primary goals was to have the joint ranges be limited as little as possible by the location of other mechanical components and the joint design itself. Figure 7 is an illustration of the FUM SCARA workspace from a top-down perspective, and its limits are described in Table 5 as well. This design results in a very competitive reach for the links and a very strong workspace. During the experimentation of the robot, a PID controller was used to test the performance along the critical trajectory determined earlier. A PID controller is designed to provide feedback to the system using a control loop to adjust and correct the robot's trajectory as it moves. The paper does not specify exactly how the PID controller was implemented, but the results speak for themselves. As shown in Figure 8, not only do the desired and actual paths line up well, but in both 8A and 8C, they lie directly on top of one another. In this presentation, in this paper, the FUM SCARA design process was outlined, including its transmission selection and its joint design. A critical trajectory was designed and simulated in MATLAB to expose the robots to its critical forces and maximum realistic limits. Experimental results were recorded and were shown to follow the simulated critical path with great accuracy, and the use of a customized bearing assembly increased design complexity to better meet project cost goals. And that's all I have. If you have any questions about the content or the presentation itself, please don't hesitate to reach out. And here are my references. Thank you so much!